let's see if this works for me. Okay, so as I first copied the this morning's session's speakers, if people have specific discussion points, and then I added a few topics to follow on the basic theme of technology and developing FRB telescopes. So let's just start with thoughts on or questions on discussions after having heard all the session talks. Any specific follow-on questions, either in the room?
So I'm curious from your perspective, what would be the most difficult part to achieve the FRB VLBI?
The FRB VLBI, you mean for the Japanese VLBI as a question, like the last speaker, we can ask Sota-san.
I mean, like in general, like the technology or the analysis, which is what is the most difficult part?
Well, I think that's a very broad question. So I'm happy to give my personal history of it. That was Jeff Peterson. 10 years ago, we talked about doing VLBI searches on the VLBA antennas because they are idle most of the time, and they have, we can just park them into blind searches. It turns out that in our view, NRIO is very difficult to deal with. They are very inflexible, and it is very, very difficult to have an experiment happen on a facility like that. So if you look at history of the 4 VLBI detections, 0 are from the VLBA, even though the dishes that detected them are similar in size. Okay, so just, is anybody from NRIO online? Okay, so unfortunately not, but this is an example of why having a rigid, inflexible structure is not good for this kind of science at all. Not that they have the same types of dishes, same capabilities. They just didn't find any, and they're not interested. Whereas in EVN, France was able to persuade the local telescope owners to just say, while they're idle, let's just do some science. And they found it. So I think that's on the strategic side. So same with Japanese VLBI. I think I encourage you to actually try it in VLBI mode, because the VLBI science return is very large. Okay, so again, I'm a bit surprised why you didn't just use the VLBI. Might as well. It comes for free, and then you learn some exciting new things. And then there's the technical question: how hard is it to localize a FRB? And of course, this is a little bit a non-standard mode for VLBI. That normally in VLBI people are used to looking at sources that don't vary, at least not over 10 minutes. I mean, whereas this thing lasts for a millisecond. So millisecond VLBI observations are done for pulsars. Okay, so this is a mode that's not totally new, but it requires the right kind of experts to actually do it. So it's not total. It's not new, but it's not routine. And I think for burst, there are additional conceptual questions even of how you synchronize clocks. Traditionally, you spend $500,000 per maser on each site, and it gets expensive after a while. That's why we're exploring other techniques. The chime outriggers will all have masers, but if you don't have a maser, this is all new directions that need to be explored.
Wei Li,
yes.
This is
yes.
about, maybe I could make a comment.
Please.
There was I can't remember the name of it now, but there was a long-running VLBA program attempting to detect FRBs by looking.
Yeah, VFAST by Adam Deller.
Yeah, yeah, exactly. Which never detected any events.
Yes, I'm happy to comment on that. So I asked Adam Deller, why did you detect no events? And he says because according to NRIO politics, they had some finite observing window and a finite amount of data they were allowed to search, and then it had to be turned off. You're not allowed to just commensally search somebody else's data. So most of the data taken by VLBI has never been searched. Speaking of, an inflexible system.
Interesting. I mean, I certainly was aware of that running for quite a long time. It's the other comment that I wanted to make, at least for the case of FRB 121102, was that the role of Arecibo was very important for the VLBI detection, and so Arecibo was operating as a part of the EVN, and the and just all of that sensitivity in one station, and I think it was Arecibo to Effelsberg, in fact, that was the baseline on which that VLBI detection was made. Having a very sensitive baseline, makes the VLBI detection a lot easier. And when that happened, I was actually quite surprised at how quickly they were able to make the detection. But I think it really was driven by the fact that just with Arecibo alone, they had the autocorrelation detection.
I think this is why the current designs for these searches, and since you listed this plot, this n-squared issue, if you have just one big station and a bunch of small ones, there is no n-squared. You search a big station for FRBs, and then you only have to do, well, then you're done. And so that's why Chime and Burst don't really have this problem. There's no n-squared to think about. And by the way, anyone here who uses VLBA, apparently NRIO says we're not stopping your science at all. Any observer can voluntarily contribute the data and continue to be searched by vFaster. I think nobody knows that. Unlike any hotel room where you get a little note saying that if you want you can not change your sheets. Jeff, you use VLBA. Did you know that you can contribute your data for science, FRB science? You probably didn't know that.
No, I wasn't aware. I actually thought they had shut the project down. Yeah, I don't know. I will have to go back and look at that. I thought they had accumulated a fair amount of data that they had searched.
They did search some data, that's certainly true, but they also stopped searching many years ago, and nobody knows, that you certainly did not know that every observer can still, it's the same system, right? It's the same correlator, it just disabled that flag, and every observer is allowed to enable it at their own request.
Mm.
So next time, you know what to do.
Sure. I will look for that in the future. A single 25-meter antenna doesn't have a, it's not a very big field of view, and it's not very sensitive, right? So it was not an optimally designed experiment. It was very clever, of course, but given what we know now from Chime and ASCAP, what it takes to, and DSA as well, what it takes to make a lot of discoveries. That is.
I'm going to just point out here that there have been 0 FRBs blindly discovered with VLBI. So there are 0 VLBI localized non-repeating FRBs, which the VLBA still had and still has the opportunity to impact non-trivially, even given the expected event rates. It's not like a 1% chance, it's actually an all-unity chance if you had kept running. And I think they just shot themselves in the foot. But we've got a question from Curtin, which I think is more useful than our ranting about NRO.
So this is actually one of the VLBI, so my hand up. The VLBI discussion was dying down. I actually wanted to bring up to do with future technologies and the importance of understanding the frequency dependence of FRBs, but maybe we can delay that until the VLBI discussion is finished. I don't want to interrupt.
Well, I think we've got multiple topics. So you would like to ask about wider multi-octave band searches for FRBs? Is that your topic?
So it's driven by the point that the frequency dependence on ensemble of FRB bursts does also tell you something about the emission mechanism, right? So if you get 1,000 bursts measured by China, 1,000 at L-band, 1,000 gigahertz or whatever else, and we look at the rates, that should be telling us something about the emission mechanism. As well as looking at the broad range components of each burst, right? I suspect it says something quite different about each one. We had Praveer's talk yesterday about the open minor observations by parts, and that was really interesting. So that the individual bursts, just the frequency image, and then also the point that got raised to get which speaker it was. I think it was the last one, observations in Japan, about different astronomical sources do have different frequency dependencies, and partly this is we need to make sure that future FRB systems do cover up frequency ranges, but it also means we need to understand those systems well enough, because this is something that China was finding. There's a very complicated interaction between FRB searches and their frequency dependence and band occupancy. For instance, if it's a narrow band thing, then it can easily get rejected as RFI. And one of my colleagues here was just pointing out the China sample that a lot of the repeating fast radio bursts, while they some of them might not have been accepted as a burst if it wasn't for the fact that the DM and decision coincident with the previous one, because they were so narrow and you couldn't necessarily identify them otherwise. So I think it's quite a complex problem to learn about this. And I'd just like to raise it. I don't know if anyone else has opinions about it or anyone else is going to work on this in a dedicated way, but I think it's important.
I'm afraid I don't think I followed the whole, if someone in the room followed more than I did on the question. I think you talked about wider bandwidths, but I'm not quite sure.
I'm sorry if this is too educated. I don't know what's going on with my microphone today. Maybe I'll switch my laptop for future discussions.
Okay.
I'm trying to be question this
By the way, if it is about wider bandwidth, there is, Chord is being built, coming online with a 5-to-1 bandwidth, and from 300 megahertz to 1.5 gigahertz. And there is, of course, the obvious restriction that your field of view changes by a factor of 25, meaning only 4% of your events will actually be detectable across the whole band. Anyways, but it'll have more than 25 events, so there'll be a small subsample that does have a wideband direct search. So I think at least on that part there will be data. Okay, I don't know if anyone in the room had or online was able to quite follow that thread. I'm happy to take feedback. Okay, nobody's spoken up. So maybe if we, just one more chance for discussion points on the presentations themselves.
So this is a kind of follow-up question to Xusen's talk. You mentioned repeater, most closest repeater, which has 4 pulses, and you mentioned it is likely from an old system like pulsar, right? So could you tell us more about that? So recycle pulsar, relatively young recycle pulsar. You mean so you mean that this FRB is powered by rotation?
So actually, it's this idea that the neutron star show life and recycle and with high peta. So maybe whether you can explain more with the physical mechanism later.
Mm-hmm.
Sure, I'm happy to explain my interpretation of what I feel are kind of obvious things that people, I don't know, obvious things that I think people don't tend to want to use as part of the information input. But first of all, this localization, VLBI, to a globular cluster is a game changer, because it actually tells you something. To only know that it's in a galaxy, okay, you need a lot of localized samples, probably thousands, before you can make some statistical inference. But with one, if you know it's in a globular, then a lot of things seem suddenly incredibly unlikely. So we know that in the globular cluster, the youngest object anybody's ever found is about as old as the universe. Billions. The age is billions of years old. There are no young objects in globulars. Now, and then you've got the energy issue, and that's why I'm just trying to say there are some, and you have to explain why, because there are very few stars, as a fraction of the total number of stars, if we think that neutron stars are related to it, there are very few in globulars in the whole universe. So the chance to find even one, and especially 1 out of 4, and in fact, for the other ones, we just don't know where they are, even with VLBI. They may all be in globulars, they're just too far away, you never know. This is the only one which is close enough, and your VLBI, that you would even know the answer, okay? Maybe all FRBs are in globulars. So this is, first of all, why VLBI is a game changer for nearby objects. If it's such a one, even VLBI, you're not going to know much. And the energetics is, and you have to explain why there are no FRBs in the globulars of our own Milky Way. Why do you have to go all the way to M81 to find an FRB? So it has to be a rare object. And then the energetics, people say, it seems to be so incredibly energetic. Actually, the energy output of a neutron star, of a rotating neutron star, is equal to the kinetic energy divided by the lifetime, the spin down time. Now, typically, in globulars, the neutron stars in our Milky Way that we see have spin down times of billions of years. And I'm going to say that, well, there may be a selection effect. Okay, that if you have a, and we know why they're spinning. They're spinning because they're recycled in a globular. If you were to recycle something with a short spin down time, because it has a larger magnetic field, for example, and we know there are plenty of neutron stars with larger magnetic fields, the ones we see all have tiny fields, those will be short-lived, and you just don't have any. If you have a neutron star with a spin down age of 1,000 years in a globular, that you will just miss it. Okay, only once per million years in our Milky Way would we see one. Right now there aren't any, and you don't expect any. But somewhere out there will be those, and they'll be very, very bright because they'll be 1,000,000 times brighter. They have to be 1,000,000 times brighter just from the energy output. So it seems to me, why isn't that just the obvious? A short spin down age object that got recycled in a globular, you have these collisional recyclings that don't happen anywhere else. So it seems that there is kind of, so rather than inventing exotic physics and creating young magnetars, I'm going to call creating a young magnetar in a globular cluster an exotic process for which there's zero evidence. Nobody's ever seen a supernova in a globular. It's never been seen, and you can invent them, but you really have to go out of your way to hide why you never see them. But whereas the other things we know exist, we know that if they're the short-lived ones, probably existed in our Milky Way too, but you're going to be lucky, you're unlikely to see one, and then you're done. So I think this is a smoking gun signal for us. It was a really simple, just the obvious, that we should we should think more about it.
I see. Thanks. Another question online?
We have a couple of online questions. One from Stuart Ryder and one from Geoffrey Bower.
Hi everyone. This is Stuart Ryder from Macquarie University in Sydney. I'm involved in optical follow-up of the host galaxies of fast radio bursts that are found with ASCAP. There's something I'm a bit perplexed about with the VLBI and particularly the outrigger facilities, both CHIME and BURST, in that your goal is to get to spatial resolutions of the order of a few milliarc seconds, which is wonderful. But you've got to bear in mind that the best possible spatial resolution we can currently get at optical and infrared wavelengths, whether it be from ground-based adaptive optics or from space, is typically no better than 100 milliarc seconds. So there isn't much point in trying to do a lot better than that, because we can't, it doesn't tell you anything more about association with objects in these galaxies. I think you might be better off going for shorter baselines to hit that sort of 0.1 arc second spatial resolution, and probably boost the number of FRBs that you'll be able to localize, rather than going all out to reach spatial resolutions that we can't currently match at any other wavelengths.
Well, so we had this long discussion in CHIME and not anymore afterwards, and there's some simple facts with VLBI. There is no additional cost per distance. Okay, so it's not as if I put it 100 kilometers versus 1,000, there's no cost savings. You're not going to dig a fiber over 100 kilometers. Well, you could, but that gets very expensive. So you could be running VLBI mode for any of these distances. And at that point, they said, well, the resolution comes for free, so why not do it? And sorry, but I'm going to disagree a bit about the localization. I'm going to go back to this global cluster example. That even though the resolution is not 10 milliarc seconds, the centroiding is. So that supposedly the FRB is displaced by something like 10 milliarc seconds from the center of the globular. Okay, and this is, you may say, oh, therefore it's not a neutron star. Because the collision rates in globular clusters are dominated by the central core, and this is now known to be outside the core, even though the core is much smaller than the resolution of your optical telescope. But that's fine, you can centroid it to easily a tenth or better than that, as truly, and now we have got this mystery of explaining this tiny offset. And again, I'm happy to continue speculating on our picture, that if you have a close encounter, the star comes in at the dispersion, and a neutron star at rest in the center by linear momentum conservation has to pick up, because at close encounter you got a parabolic orbit, star comes in and goes back the opposite direction. Okay, that's what always happens in a close encounter, meaning the neutron star has to pick up the momentum going around and leave the core at roughly the velocity, half the velocity dispersion, because it's got double the mass. That's conservation of momentum. So it'll be expected to sit at the half-light radius and not the core radius. And that's where it is. So I think this is amazing information that you wouldn't have had without this milliarc second localization. So I think there's great science to be learned and no cost. Why wouldn't you do it? And the FRB rate does not increase by having shorter baselines, because it's centrally dominated. You're doing all the detections on a main array, and it's not as if you have to search a trillion beams. Okay, if you search your VLBI beams, I think Jeff's going to tell you, good luck searching your VLBI beams. You're not going to do it at any baseline length. Doesn't matter if it's 100 kilometers or 1,000, you just forget it. So it's going to be centrally triggered. So there is no cost, there's a huge gain.
My question was related, which is, I was thinking more along the separation between an arc second and a milliarc second. And I think when we first started working on localization, the barrier we wanted to overcome was the ability to place an FRB in a galaxy and have a convincing association with a galaxy. And for that, it's around an arc second localization that's required, and and you might get some precision that's an order of magnitude better than that. And there, to go to your point, Wei-Li, there is maybe a difference in the design, right? You might go from things that have a scale of tens of kilometers to something that are hundreds or thousands, and your instrument might be different. So I think it's, for me, the question is, you get a lot more science by having the VLBI baselines as opposed to having something that delivers arc second resolution. And I think certainly the point you made about the precision, and in the case of 121102, the exact coexistence with the persistent radio source is quite important, you know, down to the parsec scale, right? It's not a chance alignment on that scale. It argues, I think, for the strength of that milli-arc-second association.
Right, thanks, Jeff. We've got a question in the room.
Not a question. I'm just a comment on the milli-arc-second localization. So about the milli-arc-second localization. So it may be important for the galactic FRB detections, and it may resolve down to AU scale or something like that, and resolve the scattering in the interstellar medium, and will be very interesting for the galactic area. So that's just a point.
Oh, thank you for the comments. I'm the biggest fan of VLBI scintillation measurements, as Dan knows, and we have probably 5 experts in this room who couldn't agree more with you and were spending their lives doing exactly that. I think Daniel, what was Daniel?
He's not here today.
Oh, okay, so anyways, there are people who were in this room who were experts on exactly that, and in fact, in the back of my mind, that was part of the motivation that you get extra science at 1,000 kilometers, because that's the baseline you need to resolve galactic propagations. Not resolve, to be sensitive to them. You don't resolve anything at those baselines yet. So yeah, so indeed, I think there's huge potential in VLBI scintillation measurements that come along with this data set. Yes.
There's one comment from the audience. Actually, this is Clancy from Clancy. We had a discussion with Clancy before, and then he wanted to clarify the point. Let me read. The frequency dependence of both an ensemble of bursts and individual bursts is important for emission mechanism. When we discussed with Sota, Ikebe Sota, we discussed the frequency dependency of FRBs. And then he's saying that, okay, so frequency dependence of FRB is important for both ensemble and the individual one. And also there is a complicated interaction between frequency dependence and such algorithms, usually not at the low detection stage, but certainly at RFI rejection stage. So this requires complicated modeling to ensure no detection bias creeps in. So therefore, he's asking, my question then was, who is interested in putting serious work into this because serious work is needed? So this is what he wanted to say, I think. At that time, his voice was not clear, so.
Yeah, oh, thank you, thank you. By the way, I think a few things that will be a moot point with VLBI, which is the possibility of interference, microwave ovens or otherwise, okay? There is the near field for a VLBI baseline is like the edge of the solar system. So anything, you know, I think there is no possibility of RFI confusion once you have VLBI data. So I'm not worried at all about you know, in the early days, we remember the history of from Dunk of, you know, if you only have a single dish and we're way beyond that. I think we're no longer in that risk. I think even the ASCAP baseband dumps, I don't think have any of these, or the aperitif base, you know, all the current ongoing experiments and future experiments, I feel, have completely overcome this confusion issue of something else looking like an FRB. And again, the multi-frequency bandwidth, I think, is still a point about the emission mechanism, if you want to understand. And in some sense, indeed, you know, we know that some FRBs are very narrow band. That the spectral index is kind of an odd way to describe them. And sure, wide band's always good. And I think we do need to move on to the next session, in fact.